Welcome to our mini lecture on linear regression. This is going to help you with part 3 of the course project, actually question number 3. So for this tutorial, we are going to be using actually our sleep data set that we've been using so far throughout the entire project. So what we're going to do is we are going to look at running just a simple linear regression, and in this case we are going to use one and then multiple variables to see if they can accurately predict age based on the data that we've gathered. So to complete this analysis, we go up to analyze, and then down to regression and linear regression. Now in here we want to predict age, so that becomes our dependent variable. Now what we're doing is we're going to actually run a couple models. The first model, we are just going to use weight, and then we are going to put both weight and height to see if using both weight and height are better to help us predict age. Now if we go up to statistics, we're actually going to want to click a lot of these, and I'll explain when they come up here in our output why they're important. Now down here, the case-wise diagnostics helps us identify any outliers in our data, and it's set to 3, but I'm going to set it to 2 standard deviations. And again, we'll see when we get our output from SPSS how it judges what data points might be outliers. So we click continue, and in your textbook it does talk about certain plots, but for this mini tutorial we are not going to look at any plots. So then we're going to go ahead and we're going to click OK, and SPSS is going to produce this output. Now if you scroll down, there appears to be a lot of output, so let's kind of look at it a little piece at a time. So it tells us right in the beginning our descriptive statistics, which gives us our average for the age, weight, and height of our data set and our standard deviation. Now hopefully everyone's curious as to why there's not 271 data values. That's because only 219 data values in this data set contained both age, height, and weight. So we did have some that were missing 1 or 2 of the variables. So now if we look at the correlations, we can see that when we did our correlations in question 2, these are the same correlations we came up with. And so as we look at these, obviously correlating age to age, you are 100%. And so if we are looking at predicting age from weight and height, we can see that predicting age from weight is only correlated at 0.154, and height's actually a negative correlation of 0.013. And everything we've learned about correlations, these are actually very weak correlations. So that's one note off the bat that says this is probably not 2 variables, height and weight, that are going to help us accurately predict age. Now this next table shows us that we entered weight first and then weight and height. So if we go down to the model summary, this is probably one of the more important ones, as well as the ANOVA testing. We can see that in model 1, which was we were trying to use weight to predict age, we have an R value of 0.154, and an R squared value of 0.024. Now again, R is our correlation coefficient, which means this is a very low correlation, which tells us there's, using weight to predict age is probably not such a good idea. Then we look at our R-squared value of 0.024. And again, that's going to tell us how much weight predicts age. And in this case, only 2.4% of a person's weight actually helps to predict their age. So and then again, looking at Model 2, once again, these are very low values. And so with this model that we've created, we can tell that we are not accurately going to be able to predict age just based on weight and height. All right, so coming down to the ANOVA testing, the category with the F, that's our F test statistic. That's really what we're looking at to make sure this model is going to fit. We're looking for a very high F value because if you look at the mathematics of calculating the F statistic, it's basically the proportion of a good model to a bad model. And so with a low F value, and these are actually low, I mean, we're looking for F values that are 80, 90s, 100. This tells us that this model is not predicting age based on weight and height very well. We also see off to the far right our significance, and comparing them to our p-value, they're both greater than 0.001, which again is telling us that this regression, linear regression that we've put together is really not going to be a good prediction of height and weight giving us age. So if we come down here, if we want to still produce a linear regression equation, and you can produce a linear regression equation using any variables you want, how significant and how accurate they're going to predict is obviously, what this is telling us, but we can still run any linear regression equation that we choose. So if we come down here, we will see in Model 1, we only had our input of weight, and then in Model 2, we had weight and height. So if we're looking at analyzing this linear regression equation with age as our output and weight and height as our inputs, right here in our unstandardized B gives us our equation, and gives us our coefficients for our variables in our equation, and I'll show you that in a minute. Also, if we look over here, we can see that again, we're looking at Model 2, which considers both weight and height. We can see our p-values are greater than 0.001, which means, again, this model is not going to be a good prediction of age. So it tells you in the next box here which variable was excluded when we ran the first model. Again, we just ran weight, and then we included height in the second one. Now, we're going to leave the next table, but I want to look at case-wide diagnostics, and this tells us when we put in there that we wanted to look at or have cases that were more than 2 standard deviations away from the mean, or outliers. This case-wise diagnostics table is going to tell us that in our data set, we actually have these 5 cases that fell above those 2 plus or minus 2 standard deviations. And it actually makes sense because if you look at the ages, it's basically our 3 higher ages, upper ages in our data set, and then our 2 lower ones. So what this is telling us is that in our model, in our linear regression equation, if we inputted the height and weight, our model, our regression equation, would predict 4156, but actually the age was 70. And so these 5 cases were what we consider outliers, And you can see your standard residuals being plus or minus 2 or greater standard residuals away. Right? And the last one, the residual statistics, basically tells us that our model is predicting a minimum and maximum with an average age and our standard deviation, but we have very high residuals, basically between negative 25 and 41. And what a residual is basically an error. And so our model is off by negative 25 years and positive 41 years on some of our data. So those are very high residuals. All right, so going back, looking at our next slide here to finish this up, here's our regression model equation. Again, I pulled our B values, our constant, and then for the weight and the height. And the last thing you need to do is test. So given a height of 170 and a weight of 62, in our data set, case number 143 has this height and weight, but the age is actually 70. So when I entered height of 170 and weight of 62 into my regression model equation, it actually predicted an age of 41 years, when actually in our data set, the age was 70. So choosing a second testing point, I chose the height of 168 and a weight of 75, and in our data set, case number 137 has this height and weight, and it gives us an age of 41. So after entering that into our regression model equation, it actually predicted an age of 44 years, which, as you can see, is only off by about 3 years from our actual data. And so unfortunately, going back here to our diagnostics and our SPS output, we can see that using height and weight to predict age is not going to produce us very accurate results. So when you are looking at question number 3 in part 3 of the project, and you are looking for variables that you believe will impact an output variable, you need to go back and look at those variables that are highly correlated. And again, you can do what I did, and you can input one variable at a time, or you can and then input another variable, and you can have several models, and you will see that some variables will increase your reliability of the model, and then sometimes if you put in another variable, it will actually reduce the liability or the reliability of the equation. So that's something you're going to have to play around with, per se, and hopefully using your results from question 1 and 2 will give you some ideas as to what variables you believe will help predict your dependent variable. All right, so thank you very much for listening.